Welcome to Unit 3 of Unconventional Reservoir Geomechanics. I'm Mark Zoback. Unit 3 follows the first part of Chapter 7. In fact, on stress fractures and faults, we'll have a second unit continuing the discussions we begin today. We have 6 topics. Definitions of absolute and relative stress magnitudes, methods to determine horizontal principal stress orientations, determination of the magnitude of the least principal stress, constraining the magnitude of the maximum horizontal stress. Then we're going to review the state of stress in unconventional basins throughout the U.S., and a few words about how not to measure stress. A lot of these topics were discussed in my first book, originally published in 2007, published by Cambridge University Press. The book's still in print. So this is going to be at least the first 4 sections are very much related to topics discussed at some length in the book, so I'll go through them rather quickly. Of course, Section 5 is totally new. And particularly applied to unconventional basins. And I think there's a lot of insight there. So let's start with these definitions of absolute and relative stress magnitudes. In 1939, Anderson wrote a classic paper defining what he called normal faulting, strike-slip faulting, and reverse faulting. The importance of this is he was actually tying an observation of deformation or slip on a fault to the forces that cause that slip. The 3 principal stresses, the vertical stress, which results, as we'll see, from the overburden, is the largest stress when dealing in normal faulting. It's the intermediate stress in strike-slip faulting, so the maximum horizontal stress is larger than the vertical stress. And in reverse faulting, the vertical stress is the smallest stress. So as we go from normal to strike-slip and strike-slip to reverse, stress magnitudes are progressively increasing. What's also interesting in this classification is it's related to faults that are active in the current stress field. So for example, if you look at a fault in a normal faulting environment, that could be an active normal fault. If the fault moved a long time ago and has been dead a long time ago, that fault may be characterizing a stress state that no longer exists at a current site. Or another way to think about it is a given area might have faults of many different orientations introduced under different stress states at different geologic times. And the faults that are active today, if there's a normal faulting environment today, are faults that dip about 60 degrees and strike in the direction of SH max. The largest stress is the vertical stress, and the smallest stress is the minimum stress. Now, associated with each of these styles of faulting is what's called an earthquake focal plane mechanism. These beach balls on the right are associated with different kinds of seismic wave radiation, characteristic of normal strike-slip and reverse faulting, and we'll be talking about that later in the course, so we don't have to divert to those beach balls right now. In a strike-slip faulting environment, the vertical stress is intermediate, the maximum horizontal stress is the largest stress. If a fault among many other faults in a volume of rock is active today, in a strike-slip faulting environment, it's a near vertical fault that strikes about 30 degrees from the direction of SH max. A reverse fault, again in a highly faulted area, in a reverse faulting environment, the fault that would be active today is perpendicular to the strikes in a direction perpendicular to SH max and dips about 30 degrees. The vertical stress is the minimum stress. This has obviously been well known for 80 years and is a very useful construct. It's good to back up a little bit and recognize the fact that stress is a tensor and has 9 components defined by the direction of traction on the edges of of a cube as shown on the left side of the diagram. We can talk about principal stresses and SH max and SH min and SV because in the Earth, it's almost always the case that one principal stress is vertical and two are horizontal. The reason for this is that a principal stress is defined in a coordinate system in which there are no tractions. So in other words, the surface of the Earth is a free surface, rock in contact with air or rock in contact with water if you're offshore, and there's no traction, no shear on the surface of the Earth. And therefore, what we find is it's very convenient and almost always exactly the case, or nearly exactly the case, that one principal stress is vertical and two are horizontal, which depending on which one is S1, S2, and S3. S1 is the largest stress, so that would, when the intermediate stress S2 is vertical, that would correspond to the strike slip case that we see on the left side. So what's really nice about this is we can describe the stress field with just three numbers, the vertical stress and the two horizontal stresses, and one orientation, which is usually the angle that S1 makes with respect to north. So three magnitudes and one direction allow us to fully describe the stress field. Now, if you're in an area of steep topography or next to a complex salt dome or something like that, these simple definitions no longer are applicable. You can look at my first book for examples of that. The other nice thing about thinking about stress as a tensor is that when you know the stress state in any one coordinate system, you can rotate the stress state to any other coordinate system for a specific application if you simply know the angles that define the relationship of one coordinate system to another. An example of this would be if we wanted to know whether a fault, which would not, could have any possible orientation, might potentially slip or not. We would take the principal stresses as defined on the right side of the diagram, and we'd resolve them into the shear and normal stress acting on the potential fault surface and evaluate whether it's likely to slip. So once we've described the stress state in one coordinate system, we can determine the stresses in any other. Calculating the stress concentration around an arbitrarily deviated wellbore is another example of how, if you know the stress in one coordinate system, you can convert it to the stress in this case, a cylindrical coordinate system of arbitrary orientation. So our job is a lot easier working with four numbers instead of 9. Turns out that there's only 6 independent components, but 3 magnitudes and 1 angle is a lot easier to work with, especially since the vertical stress is relatively straightforward. It's just the weight of the overburden, the integrated density to a given depth, Z. And for average sedimentary rocks, the gradient is about 23 megapascals per kilometer. And for a mean density of 2.3, the vertical stress goes up by about 1 psi per foot. In some areas, it might go up by as much as 1.1 psi per foot or something like that. Now, what we've done since, in improving on the Anderson faulting definition, which we colloquially refer to as Anderson on steroids, involves 4 other stress states. So these 3 in the middle are exactly the same as what Anderson did: normal faulting, strike slip faulting, and reverse faulting. But you can have an intermediate stress state in which normal faulting and strike slip faulting are active at the same time, as long as the vertical stress and the maximum horizontal stress are approximately equal and much larger than the least horizontal stress. Similarly, we can have a transitional stress state between strike slip and reverse as long as SH min and SV are approximately equal and SH max is much larger. This stress state and this stress state are extremely common in the Earth. Now, there are two end members. In this case, the two horizontal stresses are equal and much greater than the vertical stress. We'll see an example of this. It's very rare. And most importantly, this stress state, in which the two horizontal stresses are approximately equal and much less than the vertical stress, is also extremely rare, but is often thought to be characteristic of unconventional basins, which it is not. Most unconventional basins are normal faulting, normal strike-slip, or strike-slip reverse. One of these four. This is also rare. And so these four stress states are most common. And therefore, in the same stress state, you could either get strike-slip faults or normal faults slipping, depending on the orientation of the fault, in this case. Or you can get strike-slip and reverse faulting stress states, normal faults and strike-slip faults moving at the same time in this stress state, depending on the fault orientation. We'll see examples of this when we do a review of stress states in different sedimentary basins. Now, the other reason for explaining this in some detail is we're going to actually map this into our stress maps, as you will see. I introduced that in Unit 1. But we're also going to use a parameter which is referred to as A phi. Okay? And A phi here, I'll define that in the next slide, but it gets larger. A phi is talking about the relative stress magnitudes. It's lowest here, 0, increases to 0.5, increases to 1.0, increases to 1.5, increases to 2.0, increases to 2.5, and then increases to 3.0. So as you look at a larger value of A phi, you're looking at a more compressive stress state. Now, A phi, this concept results from the work of two scientists, Jacques Angelet, who was a structural geologist, trying to understand the relationship between stress magnitudes and faults. And he defined a parameter he called phi, which basically said, where is S2 with respect to S3? If S2, the intermediate stress, is at the lower limit, S2 is equal to S3, then phi is equal to 0. Or if S2 is at the upper limit, S2 is equal to S1, then phi is equal to 1. So phi is always between 0 and 1 and basically describes where that intermediate stress is. Bob Simpson, a now retired geophysicist at the USGS, came up with an improvement on the Angelet definition, and he called it A phi, and the definition is here, and he introduced this kind of algebraic expression where n is equal to 0 for normal faulting, n is equal to 1 for strike slip, and n is equal to 2 for reverse faulting. And that results in the A phi designations that are shown on each of these stress states as I walked through before. So A phi is Angelet's phi, but also then sort of made more relevant by associating with a given type of stress state. Now, the reason this is so helpful is we could use this classification from 0 to 3 and associate it with a color bar so that dark blue was the lowest possible A phi and dark red is the highest possible of A phi. And so as the color spectrum gets warmer, we see increasing relative stress magnitudes, okay? And this is a new stress map. It's just about to be published in Nature Communications by Jens Erik Lund Sne and I. And it's a map, obviously, of North America showing the orientation of the maximum horizontal stress. We'll dig into that in a lot more detail. You can see some areas of very uniform stress orientation, like the Alberta Basin, et cetera, and superimposed on a map in which the colors are indicating the relative stress magnitudes. And in the first stress map that Mary Lou Zoback and I published in 1980, based on data that was very sparse and incomplete compared to what we're working with today, we stuck our necks out and indicated that it seemed as if the stresses were increasing in relative magnitude from the center of the continent toward the north and toward the east. And now we can see that very clearly. Normal faulting in Kansas, Nebraska, eastern Colorado, sort of moving towards strike slip and Iowa, Missouri, Illinois, Indiana, and moving towards strike slip reverse in Ohio, Pennsylvania, West Virginia, and so on. And these extremely high stresses that we see in southeastern Canada are probably influenced in part by deglaciation. The giant ice sheets only retreated in the last 15,000 years, and the flexure of the crust as the entire lithosphere rebounded after the ice sheets removal has resulted in some extremely high stresses. But it's also due to large-scale crustal dynamic processes, the movement of the North American plate over the asthenosphere. And in this paper that Jens and I have written, we talk about this map in the context of sort of geodynamics, not particularly relevant to this course. But when we zoom in, we can see the same principles now applied to a stress map of the Delaware Basin, of the Permian Basin, that we published in 2017. And as I alluded to in a previous lecture, the orientation of stress is quite uniform in the Midland Basin, more or less east-west. It's a kind of a strike-slip normal faulting stress field. SH max and SV are close to each other. In some places, SV is maximum. In some cases, SH max is maximum. The Delaware Basin is distinctly lower relative stress magnitudes. It's normal faulting. The two horizontal stresses are not equal, but it's a normal faulting stress state. The vertical stress is the maximum stress. And we see this marked rotation in stress from north-south up here to northeast-southwest to sort of almost east-west to northwest-southeast and so on. And this huge rotation is very systematic and supported by lots of good data. And we don't understand. We have some ideas about what's controlling the stress state up here. We have some ideas about some of these stress transitions. But quite frankly, this large rotation is somewhat mysterious geologically. And of course, we see, this stress state and this stress state are very similar. This stress state and these stress states are very similar. We can see a rotation here that's kind of interesting. This seems sort of transitional from what's more north-south to what's more east-west through here. And so there's all sorts of things we recognize and see, a lot of consistency from independent stress indicators, which I'll be talking about soon. But ultimately, there's a lot we don't understand about the geologic origin. But, if you're drilling wells for unconventionals, you want to drill them perpendicular to the direction of maximum horizontal stress, and you can let the why alone for now and just recognize the fact that you'll use the stress information even if we don't understand its origin. Now, when we talk about stress magnitudes, we can put it into numbers for schematic purposes. And so this is what we'll do here. The vertical stress is expected to go up by 1 psi per foot, or 23 megapascals per kilometer, as I mentioned earlier. When pore pressure is hydrostatic, it's going up by about 0.44 psi per foot, or 10 megapascals per kilometer. And in the case of normal faulting, the vertical stress is the maximum stress. The minimum stress is the lowest stress. The minimum stress is always got to be greater than the pore pressure, or the earth would sort of self-hydrofrack. Okay, so, the stress state here is relatively low compression because the vertical stress is the largest, and the mean stress, the S2 is SH max, which is sort of, somewhere between SH min and SV. The strike slip case is more compressive because SH max is now greater than SV. Okay, and the reverse faulting stress regime is most compressive because now SV is the smallest stress. And under this circumstance of hydrostatic pore pressure, we can see considerable anisotropy between the two horizontal stresses. And I'm going to get back to that later when we contrast this situation with the overpressured case.